Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video, we are going to finalize the silo series by trying to apply the loads on the circular silo and talking a little bit about how to design plates, slab plates, because this was also a request from one of our dear subscribers in the past. So I think now is the time to talk about this request. Before I continue, once again, a shout out to our dear subscriber, John Al-Khani, who actually told me that, well, he did everything and his model checked out. So what gives? Well, I tried to really dive deep into it, and I thought that, well, of course, we are talking here about the idea that the deflection shape was not 100% identical in both sides. I said that, well, it's not symmetric around the both x and y axes. There's some degree of symmetry, but not 100%. But upon further investigation, I discovered something peculiar, and for me it makes sense, given my finite element analysis background. So what caught my eye, and this is why I want to give credit again to our dear subscriber, Donald Khanieh, what caught my eye was that it seems that the loads were misaligned. So I thought, aha, I found the error. I messed up my contours. But upon further investigation, if I click this, the load application is perfectly fine. The misalignment is in the mesh. The mesh seems to be misaligned somehow. It seems to be like inclined a little bit. I have the impression that the number of points on the right side are a tad bit more than the number of points on the left side. That's why you have this inclination. And it is this inclination that made this little difference in the deflection shape. Of course, we're talking about 0.5 millimeter difference. But, well, I mean, I was really puzzled because I was expecting it to be 100% equal. But, well, it turns out that there's some problems here. How do you fix that? Well, I'll have to talk about meshing later in another video. I hope in one of those projects I will have the time to do this, but today I have a handful of topics to cover. One thing I would do is to create my nodes myself. Like I just add some nodes, because if you add a node, you can control the mesher. For example, let me just show you something very simple. Let's say we go to nodes, and we want to define a node. So what's this node? It's 0.92 in Y. So let's take this and make it 0.9 or 0.85, for example, just because we want to define a node. So I hit add, and now I should have a node now, right? Yeah, there it is. There is a node now, right? Now, if you run your mesher without the analysis, of course, you see that this node suddenly has affected the mesher. So you can actually put your own nodes to force the mesher into meshing that node. So that's the first thing. Now, the second problem, or the major problem I have here, is to deal with this thing. Now, to do this, I will first of all basically, I don't know, like hide this, or just leave it. Maybe I can work around it. So what's the problem now? The problem here is that I have a plethora of loads I need to apply, and there is no good tool of applying them. Because you have, like, of course, once again, I want to refer to previous videos about the series to understand how we reach this position about loads and understanding what silos are. So, well, we have what seems to be, we have a triangular load and a rectangular load, or a triangular load and a uniform load on the slab. Now, this is easy to be done on rectangular, or basically plates, but it becomes a little bit iffy if you want to apply this on a cylinder, because believe it or not, you cannot catch any contour here. Now, allow me to demonstrate with this. So first of all, to demonstrate what I mean, now I really don't know. I need to try by the way. Let me first of all define me some nodes. So I think I defined in the Z, I didn't? Okay. Why didn't I define some nodes in the Z-axis? That's odd. I think, okay. I think I know exactly why also the finite element mesher in the previous video didn't work. It's because I have, by hand, applied this node to catch my contour, and the application of this node here, without me applying a node here, is what messed up the mesher. So an easy fix, or like let's say a note for me in the future, is when I want to apply a node to catch it in my contour application, I'm referencing my previous video, then I should apply it everywhere to not mess up the mesher, because the mesher has messed up, or I have basically confused the mesher of robot. Anyway, I will now select this node to add it to my Z-axis. I will select this node to add it to my Z-axis. And I will select, yeah, I think those are the nodes I need, right? So if I apply now, I just added some axes for the new, let's say, the significant points on the load path. Now, I'll just basically here close this, delete my measure, and try something. So if you delete your measure and try split this into a plane, just trying. So if we go to geometry, I hope it didn't work last time, so I don't think it will work this time. But let's try, why not? So if you go to edit and cut this by plane, so you can cut anything by plane. I want it to be an XY parallel plane. And this time I want to split my object, not add nodes. So let's try. If I click here and hit the apply button, the object seems not to be cooperating. It was not split. You see, it's still one cylinder. And if you run the measure, let's check if it even registered there. See, it didn't even register. It's like nothing has happened. See, robots struggles, and not only robots, humans actually struggle in dealing with curvature and curvature surface in 3D. So the idea of splitting the edit or splitting the element seems not to be really working. And let's once again try this again. I want to try all the possibilities in edit, cut by plane. I just want to go through all the possibilities and make sure that I cannot do anything. So let's go to XY. Let's try this again. I was expecting to have 2 points on those edges. Let me just see if it works or not. So apply. I should get 2 points, right? Well, that's of course, that's because I wrote a divide contour edges. This is not what I want. I want to create a node. So was it created? That's a big question. It wasn't. It didn't even register that. Well, cool. Cutting by plane is not the option you can do because robot seems to struggle when dealing with curvatures, similarly to humans. So why do I want to do this? I'm referencing the previous video because I have a problem in applying loads on this thing. I need to apply a triangular load, a linear increasing. Of course, remember, this is only an approximation of a curvature load. So a linearly increasing load and then a constant load. So I cannot even select anything here to make a contour out of it. What I'm trying to say is, well, you don't have nodes on the cylinder to make a contour off. And the more dangerous thing is that even if you have those elements, the contour is not going to stick with your cylinder. It's going to be basically a planar contour, which means that, well, those ideas are, well, not working. So how can I do that? Well, you see, let me show you my plan. Of course, the idea is not just to tell you, hey, this is how you do it. The idea is that I want to show you how you would think in solving a problem like this. So, well, first of all, let me make sure that I don't have any surface loads on this thing. So I select that, click X, click apply, just to make sure that no loads are applied now, except the own weight. Going on with this, of course, I don't need a mesh now because the mesh should not exist when you are modeling. If you go here now, and well, for example, select a load and select a surface load and try. Now, contour is out of question because you don't have points to grab in those contours. So it's not really a good idea, to be honest. So if you click on contour, it won't work because you see the X is global and you have a curvature here, so the global doesn't work because the curvature keeps curving around the element. So what works in X for this point doesn't work here because here you need a Y. I mean, remember what we did here, right? In one point it was an X and the other point was an Y. The curvature makes it even worse. So what are the options that are available for curvatures? The first option is, well, uniform planar load. And this time I will choose local. Now, fun fact, previously local didn't work for contour loads, but for uniform planar loads, local seems to work, which is at least a relief. Now at least I have something to deal with, something to work with. So if you select, for example, local and say -10 in the Z kilopascal, just a random number here, and hit OK, or basically just select like this, apply, it works. It applies it in the local -Z10, so you have something to work with. Now the problem is that this load applies the load on the entirety of the cylinder. Now that's not the case because I want to apply it up to a certain height. So you would think contour, but remember, you cannot use contours. So the other thing is triangular loads, right? If you click on hydrostatic pressure, you can define a triangular load by using a gamma here. Now, I have to calculate this gamma later. I will tell you how. But let me just show you something very cool. If you just add like this blindly, because I already have prepared this for you, side basically, and hit apply, you can see you can apply a triangular load which corresponds to a water load. And this could help you. Problem is that you have to define the height, and it's measured, I think it's measured from the bottom. Let me show you. So let me first of all delete the load. Okay, delete the load, please. It doesn't delete. Okay, right click, delete. Yes. I think I deleted the load, just making sure everything is fine. Okay, so let me show you something that you would think it works, but it doesn't. You see, if you go load level, for example, the height of the water, let me see. Now, I know there is no water here, but let's say height of water, 5, and click add and apply to the cylinder side, you get this abomination, which means that you are applying the load at a height of 5 meters from, it seems to be from the ground, if I am not mistaken. Let me just double check. Yeah, I think it's from the ground 5 meters. I think that's the case. So, well, it's kind of really annoying, and you need to focus while you're dealing with this load. So that seems to be a challenge. But what if, that's where my idea comes into play. What if you delete the cylinder and draw 2 cylinders instead? So not 1 cylinder, just draw 2 cylinders. One of them, or even 3, one of them should carry nothing, which is the cylinder on top here where no loads are. The second one should carry the triangular load, and the third one should carry the uniform load. This is how I will do it, by the way. So I'll draw me 3 cylinders, but now I need to make sure that I don't mess up my mesh. So let me show you what I mean by this. If you click on mesh the structure, you notice that there is a specific number of elements on the rim or on the side or the perimeter of the element. Don't mind those scales. Let me just adjust the scale. The specific number of elements on the side was determined when I drew the cylinder way back 4 weeks or 3 weeks ago. Now I have to remember this because I need to make sure that my discretization of the elements is going to be the same. So how many elements do I have on each quarter? I have 1, 2, 3, 4, 5, 6, 7 elements on each quarter. Let's keep this number in our brains. It's 7 elements in each quarter. So okay, let's first of all delete. I mean, it pains me, to be honest, to delete something I worked so hard for. But well, let's delete this thing. Also, I'm gonna delete all loads because, well, there are lots of loads I have tried to apply, so I'll just delete them all because I don't want to mess up. This means, of course, that the loads on the rectangular elements are now deleted, but nobody cares because I finished explaining this, so I don't need the loads again. Now let's get back to this one. So we want to draw 3 cylinders. So how do I do that? Well, similarly to how we drew cylinders in the first place. You go to Geometry, go to Objects, and select Cylinder. Now in the cylinder, you want to have a center and radius cylinder with a height, of course. So if you click on center radius, you just have to select the center and have to select the radius. This becomes a little bit challenging because, well, I cannot see exactly where my center is, so I need to be really careful when I try to select my point. So I'm just really slowly adjusting and taking a look exactly where my point is. It's kind of challenging, but I think we got it. I click my center, and now I am doing something strange. Okay, so this is the radius, and now the height. Fantastic. Now, this is incorrect, by the way, because remember, I just want to remind you that in the parameters, you don't want any base, you don't want any top, and you want to make sure how many divisions you want on the side. Side divisions means how many pieces you are going to divide this. So I just wanted to remind you of what we did last time, just in case you forgot. All right, so once again, geometry, cylinders, or objects, cylinders, and this time we will do it right. So center, radius, and no top, no base, and 5 is too much for this little thing, so I just want to divide it by 2 pieces maybe. Let me tell you this. Look, the real way to define the side divisions is to look at your axis like this and say, okay, I have a total height of 12.5, for example, and my cylinder is 9 meters high. I want, for example, to divide my cylinder every 1 meter. So I have, for example, here almost half a meter, so I think I will only divide it as 1 piece. Later, when you draw this, you would divide it into 4 pieces. And finally, when you draw this, you would divide this into 5 pieces, just to have somewhat of a consistent mesh. I will now use 2, which means I'm dividing at around each, 50 minus 15 is 35 centimeters, divided by 2 is 17.5. So I'm dividing around each 20 centimeters. So let me show you what I mean by this. This will not be perfect, but it will still be the case. Let's once again go to center and radius and draw that. So I'll just basically give you very quickly, minding where I click. This is the first thing. Of course, I should draw from bottom to top, just in case. So I just move my cursor very slowly and carefully and click the correct center, drag it out. This is my radius, and then go up for the height. If you click right now, you have the cylinder without a top and without a bottom. Of course, this needs a thickness. I go to thicknesses, select your steel 75 millimeters, click here, and now you have it perfectly done. So that is one thing less of a hassle. So if you click now here and select to mesh, it should mesh correctly. So let's hope it does. I think it does. Yes, it did. And you see two cuts here, two divisions here. To make sure that this works, let's count the edges. I think even by looking, I can say that those are really fitting. So that's my first cylinder. Let's go to the second cylinder. Now, once again, we need to decide on the side divisions. Please notice this is not 100% accurate, but somewhat okay-ish. So it's between 12.15 and 8.15. So I don't know if I want to divide it by, it's 4 meters. If I want to divide each 20 centimeters, I would have like 5 multiplied by 4, 20 divisions, I think. So remember, I'm just doing a quick brain calculation here. Of course, you should be a little bit more accurate when you do it yourself. So I select center, radius, and height, and go here. Carefully navigate until reach the center. I didn't reach it yet. Okay, there we go. This is this. No, I misclicked. So that's a mistake. Escape. Click here again. And once again, carefully try to select the center. I have it now. So you click on the center, open its radius, and then go up the height. So you go up the height and select the correct height. So now I have my cylinder. Now I messed up because I forgot to change the divisions. So once again, not going to video edit this because this is, well, what you want to see. You want to see me make mistakes, and you want to see me how I realize I made a mistake and how I correct that. Well, here the correction is not dramatic. The correction is just to painfully repeat the entire process. So this time I'll pay attention. This time I want 20 side divisions, center, radius, and height. So let me just be a little bit careful this time. I don't want to mess up twice because of time constraints. So here is the center, here is the radius, and we go up to the height, and now we have it. So let me once again test, and this is very important. You have to keep testing your mesh. If it's incorrect, then my entire approach falls apart. I don't want to discover that my entire approach falls apart later in later stages. It seems the mesher is not having any problems, so I think I can continue. Now to continue, I will delete my mesh again. See, this is important of keep checking your mesh because you don't want to invest so much time and then realize later that, well, you messed up and it didn't work. So the final piece is this. Of course, I need to check what the height is because I want to make side divisions somewhat sensible. So the height here is, I don't know, 5 meters minus 35 centimeters. So it's around 5.7. Let's say 5.8. Let's say 5.8. So we need to divide by 0.2. So 5.8, 25, 29. I think I would be using 29 divisions. Once again, this is just an approximation. You should do it in a better way. You should calculate it yourself more accurate. Of course, here, my goal is to show you how it's done, give you ideas for the future, but of course, the true modeling is on you because in real life, it's your responsibility. All right, so if you click here, I think everything is fine. I think I forgot to add material here, did I? I think I did. Okay, that's a nice thing. I have a question. What happens if you forget to add material here? What is the material? It assumes, what does it assume? Oh, okay, nice. It assumes the last material that was used, which is nice. Still, I don't believe it, so I'll have to assign the material myself just to be 100% sure. So let's check. Yeah, I think it assigned it because it was the active material that was selected before we drew the cylinder. Now, to finalize, I need to check if I messed anything up. It seems nothing is wrong. So let's mesh. That's the thing, basically. Let's mesh, take a look on the mesh, see if everything is fine. I think everything checks out. Since everything checks out, well, let's perform an analysis. Let's be bold a little bit. So let's perform an analysis under the self-weight of the structure. So, well, let's take a look. Separate structures, I know that's not a big deal. So deflection shape, of course, I need to check out my deflection shape. Oh, yeah, you don't have loads at all. I totally deleted even the self-weight, I think. Let me just check. Load table, which is incorrect, by the way. I should add the self-weight, at least. So taking a look, yeah, the load table is totally empty. That's incorrect, so I have to go back and improve that. First of all, I'm going to save my file. I don't want to repeat the entire thing again because it seems my computer is slowing down a little bit. Also, there is some noise around me. Anyway, I'll add a self-weighted mass to the entire structure. So running the analysis again, let's take a look if it works or not. I should see some deflection shapes or something at least. So it should bulge, I think. Does it bulge? I don't know. Okay, yeah, something is moving. So I'm just checking here on the supporting structure. Something is moving, so there is obviously some force transfer, I guess. So okay, it seems everything checks out. So, well, let's continue. Now here comes the idea that I was trying to push. First of all, delete the mesh. First things first. The load was, wait, I deleted the load, right? I think it was 20, and I don't have access to my previous Excel file, so I totally forgot, to be honest. But I will apply 20. Of course, you can always go to load table and change the value. So I'll apply 20 now on the sides and 30 on the hopper, but I totally forgot, to be honest. I don't really remember. Anyway, let's go to surface, select the uniform planar load, which will work locally. Now, of course, I need to check the local dimensions just to make sure everything is fine. So the local inside is Z, which means the outside is negative Z. So if I want to apply negative 20 kilopascals, which means 20 kilonewtons per meter square, to the outside. So I'll add that, and I will select the bottom cylinder. I will select the side of the bottom cylinder. Now it seems to have applied, but I don't believe it, so I need to check. Yes, it seems it was applied. Now, well, let's run the analysis again, because I'm kind of loving running the analysis over and over and over again, because it's important to keep an eye if there are any instabilities or something developing. So it seems everything is fine. There are 0 errors. And if I open the deflection shape, does it bulge? It doesn't. Does it? Not really sure. How can I know that? Well, I'll have to basically change the scale because they cannot detect the bulge. Maybe there is, but maybe my eyes are deceiving me. So I go to basically results and just increase the deflection shape to see, because I seem not to be seeing the bulge. So let's increase the diagram scale, apply. Yeah, I think something is happening here, yes. Yeah, it's bulging. Okay. I believe you now. Yeah, that's bulging. Also, it's consistently bulging, and I have a reason for that. This is like really interesting. Why is it not bulging exactly the same on the circumferential side? Because you have supports, and those supports stiffen parts of the circumference and release parts of the other circumference. It's also the same here. So, yeah, let's normalize back and continue. Because when you have those supports, so when it bulges, it doesn't bulge out exactly the same in all the directions, because there are things holding some of the directions, so it doesn't bulge exactly the same everywhere. All right, so, and this is why I think the advice of our dear subscriber, Nia Sapai, comes into place. You see, he advised to make a ring beam around the silo. Now, this would uniformize or make uniform the deflection of the silo, because if you have a ring beam, then all the elements in the silo are confined with the same stiffness. So once again, a shout out to our dear subscriber, Nia Sapai, whose advice would come into handy here. I will leave it as is, but, well, at least you have an idea now. All right, so this is only partially all my problem. That's not all my problems. I just solved one tiny bit of my problem. Now, of course, you need to apply the triangular law. This is where the fun starts. Okay, so how do I apply this? Of course, my plan is to go to loads and go to hydrostatic pressure. I'm going to use liquid pressure to fool the robot into making me a triangular load. Now, how does the liquid pressure work? You don't have any static pressure on the top because this is open, or I'm assuming there is no pressurized air inside it. You have the unit weight of liquid, which is something I will calculate right now, and you have the level of the liquid. Now, we will use this to calculate a pseudo-liquid, a placeholder liquid that has characteristics that forces to give you a triangle of 0 and 30,000 or 30 kilonewtons. What do I mean by this? See, this is my wall, and I want to apply a triangular load where it starts at this location and ends at this location. I want it to have 0 here and 30,000 here, or 30 kilonewtons per meter square. So now I know this is from the soil or from the granular material inside the silo, but I will try to mimic or basically trick robot by using a fluid to pressurize the same pressure, because you know that fluid pressure is gamma, which is the weight of the fluid, multiplied by H, or this is the unit weight of the fluid. So now I need to find gamma, and the rest would solve itself, I hope. So how can I find gamma? Well, remember, this is not a real liquid. I'm going to mimic this as if it is a liquid. So how do I calculate gamma? At the height of H here, the load was 30,000. Of course, the question is, what is the height of H? So if you go here and click on the axis and check out your z-axis, you see that from 12.15 to 8.15, this is where the load was increasing. So your h is actually 4 meters. So my h here is 4 meters. Now, if your pressure is 30,000, you can calculate gamma, because gamma is going to be equal to 30,000 divided by 4. Now, if you do this, you will get an answer of 7.5, I think. So 7.5 is the gamma answer. But what is the unit? The unit here is kilo Newton per meter cube. Now, this is not 100% correct to be used 7.5 here, because the unit here is kilogram per meter cube. So I need to convert this. See, a lot of things happening here. So, well, let's try to convert it now, shall we? So, according to my calculations, pressure equals gamma multiplied by h. Now, h equals 4, p equals 30 kilonewtons per meter square. So your gamma equals your p divided by h. So your gamma equals your 30 divided by 4, which means it equals 7.5 kilonewtons per meter cube. This is something we established now. Of course, I want to turn gamma into a density, so I need to turn the kilonewton into a kilogram. Now, first things first, the same gamma will equal 7,500 newtons per meter cube. So I need to divide this by 9.81 to find my density. So I need to say that density equals 7,500 divided by 9.81. This would equal, well, I don't know, 9.81, 764.53. So 764.52, let's say, kilograms per meter cube. And this is density I'll be using. We want the density here to be in negative, I think, so negative 764.52. Now, it doesn't still work. Why doesn't it work? Because you want to find the liquid level H. The liquid level H is measured from the ground, by the way, which is strange, but this is how robot rolls. So if you click on this and select the level where you want the liquid to start, it doesn't select it, right? That's strange. Okay, I have to do it by hand, right? So what's it by hand? It's 12.15, I think, right? Yeah, 12.15. So if I write 12.15 here, what I'm expecting now is that it will work. So let me apply this to, no, I should delete the mesh first because I want to see things. So let's apply this to here. No, not here. Only this. Only this. Wait. I need to select. I need to be careful of my selection. Only this. Yes. And now let's apply that. Does it work? Oh, look. It does work. I think I'm kind of messed up, I think. Oh, yeah. I messed up. I said 30. For some reason, it's 20. Oh, that's annoying. Still not going to video edit this, but let me show you what... Okay, I messed up. I made a mistake, but I need you to see. You see, when I applied the force, I saw that the load doesn't align. I was thinking those two loads should be equalish. I know I made a small approximation by saying 0.52 instead of 0.529, but still, like this big difference, I was annoyed. So then I started thinking, why is this big difference here? But, well, it turns out that I used 30 here, which is incorrect, because I should use 20 here. Now, if you do your recalculations again with 20 here and 20 here, the only thing you have to do to fix this is to divide this by 1.5 for mathematical reasons. So I should divide this by 1. Wait, what? Should I? I should divide this. No, I should divide this by 3 and multiply this by 2, hoping that this works. So 509.68. So this should be 509.68. I hope I don't mess up again, because messing up once is okay, but messing up twice is kind of iffy. So, okay, how do I fix that? I go to loads, load table, because I don't want to do the entire application again. And here I want to have 509.68. So 509.68. Hitting the enter key, closing the load table, checking. Yes, this checks out. This is not perfect. There is some difference here because I approximated something. This little, I'm really zooming in hard, this little difference. But I mean, come on, like that's more than adequate for my purposes. So I applied my load. The final thing I should apply is, of course, the Hooper load. I'll just apply it lazily as 30. I think that's why 30 is in my head, because the Hooper load was 30. I'll apply it as 30 here just to make sure that this works. So let me select it correctly. So there we go. Those are the two things. It selected only one, so the other one is not selected. It is selected, but those are two, right? Aren't they two? I remember I have done two, not one. That's odd. I don't know. I'm kind of perplexed. Never mind, I'll apply. And, well, it depends. Of course, I can see the results later. So this is now perpendicular. Of course, those are the Hooper loads in the local z-axis. That seems to be strange. There is something amiss here. I'm getting warnings here, to be honest, in my brain. Like, what, did I mess something up? Local z, and did it apply correctly? I cannot see from the outside, so it's kind of annoying to see in the inside. I think it did. I'm not really sure. I can not detect it. Why am I thinking too much? Where is the local axis? There we go. Here is the local axis. Let's take a look. Oh, wow. The local z. Wait, what? Well, that's a surprise. That's correct. No, I don't know. This is the local z-axis, right? So I think we're doing it right. I think we did it right. I have. Let me just check. I think we did it right. Well, I'll trust Robot basically, because I mean, here, this is the z-axis. I want negative local z, so I'll trust Robot on that, because like I don't want to stay ages here. It kind of annoys me to skip something, right? Wait, it's just against my nature. So, well, let's just group something. So let's create this, and no, let's create a group out of this. Show me only the active ones. Okay, now I think I can see now. Yeah, okay, it was local. I think I just freaked out for nothing, it seems. I see two forces. Or is it one force? Are there two forces? That's really a mystery for me. I can see two forces. I think that's the reason why I freaked out. Okay, so loads, load table. Let's just get down to the bottom of this. 50. Like this is this is really breaking my brain now. This is 50, right? So 50. Okay. And let's go to load table and see what are the loads that target 50. This is the self-weight. This is 50. This is the one that targets 50. It's in the local. This targets the side. This targets the side. There's nothing else targeting 50. So what gives? Why is Robot doing this strange drawing for that? Is this a bug? Are we dealing with a bug now? Because that's kind of strange, truth to be said. Do I have an explanation for this? Do I have one? I don't know. Like, it's kind of strange. What is this, what I'm seeing? I think I have an explanation. I think I do. I think this load is applied on this side, and this load is applied on this side, just because it's discretized. Look, this is the piece that is discretized, and this is perpendicular to this piece. And the other load is perpendicular on that piece. Well, this is the numerical approximation of finite elements, because you're splitting your cylinder into finite elements. So I think that was false alarm, my personal opinion here. So I don't know. I think everything seems to be fine. So, okay, let's just continue. All right, if you run the analysis now, and I want to teach you that you should sometimes just take a step back and second guess yourself to check if everything is right or not. If you run the analysis now, well, what happens? I don't know. Let's see the displacement, basically. So if I go to refresh everything, open deflection shape, increase the deformation scale, basically, and take a look if it bulges or not, because I'm expecting it to bulge. It does, I think. So let me just tap 1, 2. Yes, it's bulging. You can see that when I toggle deflection and non-deflection, it bulges. It bulges only slightly because I was expecting to have more, truth to be said. I'm expecting more than this. Displacement is almost 0. It's like half a millimeter. Is this true? So this is 5 times 10 to the power minus 2, so it's 5% of a millimeter. This doesn't make sense. Okay, first of all, you have served your purpose. So because this is affecting my scale, I'll delete it first of all. You can, of course, check it later from previous elements. So let's just recheck our entire thing. So analysis. I'm just a little bit annoyed that the deflection is too low. I was expecting more, to be honest. Maybe it's because it's a cylinder, but I need to get down to I need to convince myself first. So deflection is 0.2 millimeters. Huh. That's really small. Oh, yeah. Okay, now I'm convinced. You see, I was a little bit annoyed. Now let me get you some ideas. Let me just put you in my head now. I was kind of annoyed that the deflection was too small on the silo in comparison to the concrete silo. I totally forgot that the elastic modulus of steel is 10 times the elastic modulus of concrete. So it is totally okay and expected for the steel silo not to bulge a lot, because the elastic modulus is higher, which means it is more rigid, eventually meaning that deflection is smaller. And that's the reason why I need to increase the scale into unbelievable scales to somewhat see the deflection here. Once again, you can see that it doesn't bulge out equally. If you go on top view, you can see that it bulges out here a lot and bulges a little here. The reason behind this is being that you have supports somehow here that, of course, those supports are now moving aside. Now, don't like get worried that the supports move so much. They don't move so much. I just increased the scale of the deflection so much that the supports just don't make sense anymore. But I needed to do that because I wanted to see if the silo bulges or not, which it does, and I'm happy now. But I was unhappy because the deflection seemed to be too small, but there is a reason behind it, so no worries. All right, so fantastic. I think I've done the analysis part, so to the design part. The design of the substructure was covered in the previous video when we did the concrete one, so I'm not going to talk about this. What I will talk about today is design of the steel silo shell or the steel silo plate itself. Now, how do you design steel plates? Now, believe it or not, and I have the AISC in front of me, and this is an available version. available on the internet by the AISC itself. It's the American Institute for Steel Construction, and it's basically the code that I use to design steel. And believe it or not, the code doesn't talk about steel slabs because it's unheard of. For it, it talks about design requirement, about strength and serviceability requirements. It talks about compression members, and it means by this compression members steel shapes, steel sections, tension members, flexion members, shear, torsion, combined loads, composite members. This is members when you have concrete and steel together, and even the composite diaphragms. It's a composite, basically concrete and steel. So a corrugated sheet, for example. It talks about steel connections. So from the get-go, just very quickly, a quick look on that, seems not to be dealing with a steel slab itself. Now, this doesn't mean you don't have any tools to design those things, but it becomes kind of your own sense of it. Of course, for the dear viewers, if you have any other code, for example, the Euro code or the British Standard or the Indian code or whatever, if you have any code that has specifications for plates, please tell me in the comments because I'm really interested. I might even miss something here, but as far as I remember from my studies on the BSc level, there was no real chapter that talks about plates. So to deal with this in a sensible way, you have basically two options. Option number one is to take a piece of width 1 meter and deal with it as if it is a beam or an element under loads. And this is the typical thing that you use in classical calculations when you want to design any slab, concrete or whatever. You take a 1 meter strip of width and check out and design this 1 meter width or 1 meter strip. So how would you design that using the classical method? Using the classical method, you would go to results and select maps and, well, basically go, for example, for M, moment, XX. And you can see the moment XX here, which is kind of, I don't think, okay, there are stress concentrations here. I can see them. It's kind of annoying, to be honest, but it's there. But generally speaking, without the stress concentrations, if you want to ignore them for now, the general design here is to basically design according to those moments. So you take the moments here in X. By the way, X is horizontal. And you take the moments here in Y, which will be the significant moments, as you will see, which have higher values now, and design your member based on those moments. Furthermore, because this is a perfectly circular cylinder, you will have stresses in the XX direction. I think I clicked on open new window. I don't want this. You will have stresses and axial forces in the XX direction, which is basically the tensile and compressive forces. And you can see that you have tensile and compressive forces on the element. Now, tensile on the cylinder seems to make sense, but why compressive forces? Why compressive forces on the hopper? You see, when this bulges out, bulging out compresses the hopper, and that's the reason why you have a hopper under compression. It's kind of, if you have a long cantilever, then the beam inside the cantilever will bulge up instead of down. Once again, this is the hotspot of your design. It's basically where you have the connection here, and it was able, you see, having this plate was able to divide the stress into two pieces, but still you have a stress concentration here. This is the danger zone. No relationship to the danger zone of Top Gun. All right, so how do you do that? Now, of course, you can use 1 meter strip, or you can basically use stress analysis. Now, how do you do a stress analysis? You see, you studied in mechanics of materials something called the equivalent stresses and the principal stresses. If you have an element that is under stresses, then of course you have stresses in X, you have stresses in Y, and you have shear stresses, and those stresses will basically create you principal stresses, which will give you the maximum positive and negative stresses on an element. This is okay, and you can use it for design. However, there is even a better equivalent stress. I'll get to that in a moment. So allow me to explain this. This is going to be a little bit theoretical, so please bear with me. Let's say from mechanics of materials that you have, and I teach this, by the way. Let's say that in mechanics of materials, you have this stress element, okay? And this is under compressive stresses like this. and tensile stresses like this, and some sort of shear stresses like this. Whatever the numbers are now. The numbers don't mean anything to me. It's just a little quick refresher. Of course, this is a general case of stress, and of course, you can flip this or rotate the element in such a way to create maximum compressive and tensile stresses, which is called principal stresses. And if you have principal stresses, then your shear is zero, maximum tensile, for example, and compression. And you can have another element where you have maximum shear. In this case, the tensile and compressive stress are the same, and they are the average stress. I'm not going to turn this into a mechanics of material lecture. I teach this anyway, but I just want to remind you of what you studied in the university. All right, so those are the two general things you can do with Mohr circle, and this is the maximum stress you can have. Now, a somewhat simple way of doing that, which is something I do not want to do, is to say, okay, let's say that max sigma positive tensile was, I don't know, like 100 megapascals, and max sigma negative was, I don't know, 80 megapascals, and you take those two values and check them against the carrying capacity of your steel. So let me remind you what I mean by this. If you go here and go to job preferences and select materials and go to your material definition, you can see that you have a yielding stress here, or resistance here, yield, which is around like 400 for F ultimate and 250 for F yield. So you say, okay, fine, my stresses are less than the yielding stress or the ultimate stress depending on your code and design criteria. And you say, okay, everything is hunky-dory and nice. Well, this is incorrect because allow me to go one extra step. This is now master stuff, but I want to explain it anyway because I teach it too, and I want to explain it to you. Because, I mean, it's not just about how to use the software, it's to understand what you see in the software. You see, the problem with yielding and ultimate stress is that it was tested on a steel rod under an axial force in both directions. There were no forces on the lateral directions. On the lateral directions, there were absolutely no forces. You had only a uniaxial test. Now, this is contrary to what you see in the material, because in the material, you have sigma x and you have sigma y. So the F yield you get from the test is actually not going to be sufficient to deal with this, because this is a biaxial state of stress. Allow me to remind you of something in soil mechanics. In soil mechanics, you had the triaxial test, where you had a soil specimen under axial force, compression, and under hydrostatic pressure on its sides. And you know that the hydrostatic pressure had an effect on the load carrying capacity of that soil specimen. Now, I'm not going to make this become a soil mechanics lecture, but I want you to remember this, that the lateral pressure, the hydrostatic pressure on soil, had an effect on the soil carrying capacity. Similarly, the hydrostatic pressure, or in this case, the pressure in the other direction, will have an effect on the load carrying capacity. Taking each sigma on its own is okay, but is not really accurate. You need to use those both sigmas to get one equivalent stress. This is called the von Mises stress, and it's based on the von Mises failure criterion, something I will only show a picture of because this is master and PhD stuff. It's basically an equivalent stress that somehow tries to mimic this. So I want to show you very quickly, for the interested among you, how the von Mises stress is and what the von Mises failure envelope is. I said this before. You think I'm just talking nonsense to impress you, but no, this really exists, and allow me to prove this to you. Here is the von Mises failure criterion. Of course, the von Mises equivalent stress, this is the von Mises surface of the failure criterion. And the von Mises stress, as you can see, the equivalent stress has sigma 11, sigma 22, and other sigmas. Now, sigma 11 is sigma in x-axis, in principle. Sigma 22 is sigma in y-axis. Sigma 33 is sigma in z-axis, because this is a triaxial tensor. If you go to uniaxial, well, then your sigma is sigma yield. There is nothing to say here, because if you say uniaxial, then you are basically having one stress, which you compare to your sigma yield. That's perfectly fine. If you have multi-axial, then you need to find an equivalent stress. And this is really cool. Like, I have been doing this during my PhD work in Hannover in Germany. So a shout out to my dear Professor Udo Nackenhorst, my supervisor in the PhD in 2013 to 2016. Good times. All right, so it's a long story. I don't want to like really dive deep into it. It's stuff that you will study in PhD. So I'll leave it for you. I just want to tell you that, hey, in simple words, because I mean, I should explain to the bachelor level engineer. In other words, hey, lateral stresses do matter, and those are not taken into account if you compare one stress with yield. So you have to calculate the von Mises stress. Of course, this is one of the stress assumptions, one of the stress failure envelopes, and this is something like the equivalent stress that you could use. Of course, this hexagonal thing is a Tresca yield surface. To finalize, we do recommend as scientists to use the von Mises yield criterion to deal with ductile materials. This is something that we know is well established. So von Mises is used for ductile materials, whereas for rigid or brittle materials, von Mises is not really not really recommended. There is the CAM clay model that could be used for brittle material. Once again, I will leave it for you to Google. This is too much information for you for now. I just want to focus on robots. So, all right. End of the line, you should go to your results, select your maps, and select the complex stresses, and select the hypothesis of von Mises. Of course, here the calculation of von Mises can confirm to wooden armor, can confirm to, now those are basically calculation ideas for the von Mises stress, and that is the answer on one of my dear subscribers about what is wooden armor and what is even this complex thing. So now you have your answer. I'm sorry it took me so long, but this is the first time I had to use this technique. So if you click on that, you can see that the maximum von Mises stresses are actually 5 megapascals, which is a joke in comparison to the 200 or 290 megapascals steel can carry, which means I over-designed. So I need to improve my design. How do I improve my design? Well, I can apply another thickness, or I can modify this thickness. Now, I don't recommend that. I never recommend that you modify a name, the thickness without modifying the name. But I'm just a little bit lazy, so I'll just use 2-inch or even 1.5-inch material. So I'll add that. Now, because I've done this, those will automatically change thickness. This is not recommended. I recommend you to make another name for the thickness because this is a little bit misleading. However, I just want to hammer home the point, so I run the analysis again and keep an eye on my von Mises stress. Yeah, it increased a little bit. Just one thing I need to focus. The layer is in the middle. No, I want the layer. Wait, there was something I wanted to mention here. There was something I wanted to see here. Exactly, I want the absolute maximum. I want to see the absolute maximum von Mises stresses. Oh, it went down. That's odd. Oh, there we go, 10.66. I asked for, okay, let me just tell you what I did. I asked for absolute maximum because previously he was calculating the von Mises stress in the middle point. When you calculate stress in the middle point, you only see the effect of the axial forces, but you do not see the effect of bending moments. Now you can go to upper and lower, and if you go to upper and lower, then you can see the effect of stresses from moments because MC over I. However, I don't care. I want the absolute maximum, so it will automatically select upper, lower, middle, whatever to show the absolute maximum stress on the element. Now, if you apply that, you see it's 10.66 in the von Mises stresses, which is a lot smaller than your 200 and 290, and you would think, that's some kind of a waste of material. But no, I will only go down another step and use 1 inch, and then I will not go down furthermore. I will tell you why in a moment. So I'll go down to 1 inch, hit the add, hit OK, yes, and close and run the analysis again to take a look at the von Mises stresses, which would go maybe to 20, I think. I don't know. It goes up to 11, really? 1 inch, that's the difference? Okay, uh, I'm kind of like, I'm kind of surprised. But all right, so still it seems to be small, so I'm really not being economical in my design. However, no, I am being economical in my design. Allow me to like open your eyes into something that you have not seen. You see, you can go down up to maybe like 10 millimeters steel and it will still be economical. However, uh, this is economical under the current circumstances. The silo is erected and is filled with cement. But how does the silo reach the cement factory? And I want to talk about something that has nothing to do with robot now. Because for me, I think that I have achieved my objective by telling you how you design these things and how you would improve the design. So for me, the content of this video has been achieved. However, I want to chat a little bit about something else. You see, what engineers seem to forget sometimes is that they just focus on the operational status of a structure, which is in 90% of your time true. The operational status of the structure is what would determine and control the design for normal buildings. However, for silos, it's a bit different because silos are being transported into place before they are erected. So there are transportation and handling loads that need to be taken into account. I have not done this, but there is a full science of handling forces and how you can like assume a crane load here pulling and a crane load here pulling, because you would be like transporting this in a you would be transporting this horizontally with a crane, the crane that lifts this silo up. So you would have to deal with this type of load, and you would have to design this type of load, especially for structures that are being transported. Examples for structures that are being transported are precast concrete structures and silos and any functional structure that can be displaced. So I know my 1 inch seems to be an over design, but I just want to hammer home the point that, hey, yes, it's an over design right now, but I need it to withstand also handling and transportation loads, also impact loads, especially in transportation. Because if I make a steel sheet of, I don't know, 5 millimeters, it will bend and dent and have all kinds of problems when I transport this. Furthermore, you will be adding a staircase on the side, and this is something I mentioned last time. And to add a staircase, you will of course need to weld that thing. Now, to weld things, you cannot weld something to a extremely weak sheet. You need to have some material on the wall that you are welding to. So all of that are kind of practical considerations. Of course, I don't want this video to become 5 hours long, so I like to intrigue you and tell you, hey, this exists. So I hope that you have learned something new, especially with regard to the von Mises stresses, because I've never talked about them before, and it was a request in the videos. So there we go. All right, well, I think this ends my video for today, and of course, I hope that you enjoyed the video and that it was beneficial for you. If you think that my video was beneficial to you, then please like, share, subscribe, and comment. Especially subscribe because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video.